that, and I can share screen. All right, so we're in business, right? This is where I get in trouble. I said hide floating screen and it just disappeared. Right, now it won't hide it there. All right, good. Away, away, there. All right, so anyway, back to this, sorry. So these guys, anyway, so they're doing a shifting of the along the concentration, but they don't have, so it's not based on Boltzmann's law, it's just based on we can do it. Okay, and they show, like the Wagner paper shows they can do it. So they got so these are all different concentrations, and then finally they get these master curves. This is a time temperature superposition master curve. That's the AT from Boltzmann. They're using an Arrhenius function. Basically, Boltzmann is like delta H over T type thing. And then they do the same thing with concentration. So they have, these are different concentrations, and they just use a shift factor to shift the curves onto a master curve. This is for clay mixed with polyethylene oxide in solution. So it makes a gel in time. Anyway, so this is a separate paper. It just shows that you can do it. You can do that shifting, and you have some shift factor that you get from it. So anyway, these guys are going to do the same thing. They're going to do a shift factor and concentration to get their, so they call it TCS, time concentration shifting. So this is an example. So they have three rheometers. One's a cup and bob rheometer called a Couette viscometer. So you have a bob in a cup, you spin the bob, and it's like a continuous spinning usually, and you get the viscosity out of that. Like what's the torque on it for a certain speed gives you the viscosity, right? So the other one's like a cone and plate viscometer where they're doing oscillatory, so oscillating it. The third one is DWS, diffusive wave spectroscopy. So it's a dynamic light scattering. You put beads of known size into the stuff. Then from the mean square displacement of the beads, you can figure out the viscosity of the fluid, believe it or not. And you can get the G prime, G double prime as a function of frequency from it. So it's like magic. It's basically the magic method. So that's called microrheology because you're using microparticles that you throw in, you observe the motion of the microparticles. From that, you can decipher the complex modulus, basically, G prime, G double prime. So it's mystical. No one really understands how it works. It's a lot of math involved. Basically, it's like you get a correlation function for that particle. He shows in, there's a paper here, Microrheology Review. So you get I think he shows in our paper too. So our paper is pretty comprehensive. He goes through everything. Let's see, this thing should, Microrheology Review. He's got the math in here somewhere. Let's see, maybe not, maybe it's in our paper. Yeah, our paper just gives the bare essential, which is, it's kind of confusing. But it's simple enough that you can see that you can just plug and play and get the thing. So he's got this R squared, that's the mean square displacement of his particles. You see, I'll make this a little bit bigger. Does that work if let's see, there's a plus sign here. Here. Where does he do this? Oh, I guess he doesn't do it, maybe. I'm pretty sure he does it in here. He's got the math for all the different scaling regimes of the particles. I thought he gave the equation. It must be in this review paper. Where they do that? Somewhere here they give the equations in kind of a simple way. Microrheology starts there. I don't see it here. Anyway, this is just a kind of you get the DLS measurement and you get the correlation, the G1 correlation function. Then you can, from the G1 correlation function, you can get the complex mean square displacement, which you can convert to G prime, G double prime. So it's just kind of a math. There's a Fourier transform involved in it. It's called a one-sided Fourier transform. It's in here somewhere. This is dash. one side. Here we go. All right, so that's it. So oh, that just says one-sided, but before that, he shows how to get this thing. Anyway, it's not really that important. The bottom line is they can get to higher frequency with this. So you can get to 10 to the -5 hertz, 10 to the 5 hertz. This normal rheometer is going to 10 to the 2. So 100 hertz, and they can go to 10,000 with that other thing, and it overlaps. So the data overlaps here. So the line, because the DWS, it's a function, so it's like a continuous function, you don't get points. The rheometer, if you're going to measure at different frequencies, you get 1 point for each point, like the cone and plate viscometer. That's these point things, and it goes up to about 100 hertz. And depending on the temperature that you're master curving it to. And then the other machine overlaps with that and continues on up to like three orders higher, like 1,000 times faster. If you took it, so 100 hertz is kind of like AC hum, like so you can imagine like 1,000 times faster than that. You can't hear it, right? So basically you can imagine that it doesn't work. Like you can't mechanically oscillate at 10,000 hertz. So you need to do something else. And this diffusive wave spectroscopy does it. So it expands. Now, and the reason he's expanding out is because he wants to see transitions at small sizes. So high frequency is small size. So basically, this is the right paper. Microgravity study. Yeah, so he's got figure 1 is what I want. That's figure 2. That's going to move. So figure 1's is his master plot of everything. So this is good solvent, that's theta solvent. So, and he claims that his thing is theta solvent, like his PEO. So he's using polyethylene oxide and water. And he wants to see these kind of regime changes. So dilute is the blue one, and he's got just, so this is the specific viscosity, the complex specific viscosity, the magnitude of it. So it means this thing would have like the viscosity and then I times the modulus times I frequency. So basically this thing is like the modulus, except it's kind of inverse to it. It's almost like the compliance, right? So anyway, so he can get this from the mean square displacement from the DWS measurement. Anyway, so this is the kind of thing he wants to see. He wants to identify these slight changes in slope of this thing. So when he goes to long time or low frequency, he just gets basically the like intrinsic viscosity. As the concentration increases, the viscosity increases proportional to it. It just goes up, right? Because you add, it's the Zim part of the thing. So it's not the Zim part. It's just the normal flow part. We just put in. It's like the displacement law. You put the thing in, so it's in dilute conditions, and you put the polymer in, it just displaces the fluid. So the concentration just goes up. It's a constant feature. And then at this part, you get like power law fluid. So as you shear it more, so at shorter times, you stretch out the chains, and the viscosity drops. Right, so this is just like power law fluid behavior, and this is like where you're not distorting the chains. We're just doing a displacement law. You're increasing it. And then you reach an overlap concentration where the chains interact with each other, and then you introduce this Rouse mode, which is, so each of the concentration blobs of the chain are going to form a chain of concentration blobs. Then those are going to diffuse following the Rouse theory, which predicts this -1/2 slope to the thing. I can show you where that comes from. But basically, that's the Rouse prediction, is it's going to be -1/2 if you plot the viscosity versus frequency. And it would be 1/2 if it was viscosity versus time. Right? So he wants to see that. And then if it's a Zim behavior, so if you go to higher concentration, then you get entanglements. So the overlap concentrations here, the entanglement concentration is a different number. And this is something that more or less was invented by like Colby and Rubinstein, that you have a different number between where the chains overlap and where they start to entangle with each other. So there's this gap. Okay, and they've made a lot out of this gap. So before this, I guess, was mentioned, basically it wasn't made into an industry, so they kind of made this. Colby Rubenstein kind of made this gap into an industry, and the thing you can do is you can see there's like changes in the slope that you can pick up. So you can pick up this -1 is the Zim part of the thing, or the -1/3 is the Zim part. -1 is the normal flow part. Then as you go to longer times of smaller size, you see this Rouse part where the concentration blobs are moving around, and then you get to the Zim part where the chains just act as that's right. Let's see. Okay, the time scales here. Size scales and time scales. So the smallest time, which would be to the right here, is where it acts like a solvent. Then we don't see that in this curve. And then dilute solution Zim models the 1/3 part of this thing. And then it goes to Rouse, so is the 1/2 part, and then reptation, that's the 1 part. So you can't get reptation, you need to have the chains entangled to have the chains moving through a tube of entangled chains. Right. So if you're below the entanglement concentration, you can't see reptation. When you get above that, so he's saying viscosity is kind of related to concentration through something like Mark-Hoek equation. And so if you say you're increasing viscosity, you're increasing concentration. So he's got the 2 scales here, but they aren't proportional. It's by a power. It's like concentration to the power A gives you the viscosity at low frequency for a long time. Right. So this is the normal Mark-Hoek behavior here, but as you have entanglement, you get this transition to where you see reptation, where you see the chains moving within the entanglement tubes. And then if you go to higher frequency or shorter times, then you see within the tube that you have Rouse behavior, meaning that the chains act as if they're independent chains that have this 1/2 dependence, which we'll get to later where that comes from. And then when you get to below the Rouse behavior, the Rouse is made up of concentration blobs. In other words, the Rouse behavior is a bunch of concentration blobs moving through the tube, or just right. And then when you get to shorter times or higher frequency, you see the individual blobs, which are just like Zim blobs moving around in a fluid. It's sketchy. It's kind of like a pretty convoluted thing. One thing adds on to another. And then, so anyway, that's what he wants to demonstrate, that 1/3, 1/2, 1. So he's got Zim, Rouse, and then this is reptation. And then it goes to just bulk motion of the fluid, like the Einstein kind of flow, all within a polyethylene solution. You can see that it's complicated. It's not simple, right? So anyway, so he shows that. Figure 9 shows that. Like in the end, he demonstrates exactly that at figure 9. So he's got, this should be 1/3, it's 0.29. He says good enough. Then he gets the 0.5 for the Rouse part. That's exact. Then instead of 1, he gets 0.77. He says good enough. Right. And you can see like these are concentration shifted. So he's got different concentrations of polymer in order to access this wide range. Not only does he use this DWS weird machine to get to 10⁵ frequency, but he's also doing concentration shifting to get the whole curve. Right. So he can access this entire range. And then he demonstrates it. All right. So you could say, all right. So the theory kind of agrees. The numbers aren't the same. Or you could just say that's some kind of decay curve. Or you could say there's power laws there. So it's right. In other words, what's the significance of this? Is something you should ask yourself at some point. Colby and Rubenstein have made a living off this, but I'm not sure that, if you're making shampoo or something, like how important is this? I don't know. It's kind of hard to tell. You could fit this whole thing with just some kind of polynomial or something if you wanted. So that's kind of the issue here. It's like you dig a rabbit hole, and then it seems like it branches off to different things. This is a good example of how far do you want to dig? Right? If there's still gold there, you keep digging, right? But basically, at some point, the amount of gold in the rock isn't worth digging anymore. I was reading about the Johannesburg gold mines, the Lesotho guys are down there because they ran out of gold for industrial production, but these guys are still going there, and then they have gangs, so they're still making $100 million a year off these dead gold mines in the city of Johannesburg. Like the city's built on top of the mines, and they're killing each other. Like 15 people were killed a couple of weeks ago, listening to the accordion music. Like they play anyway, Lesotho, they play accordion. They do some kind of rap music thing with it. Anyway, that's a case of like, to Colby and Rubenstein, this is still worth digging, but to the industrial world, maybe we've reached the limit of it, So anyway, it is a good example of kind of what, so you have to read these books with a little bit of grain of salt. Like, is it really worth my time to do this, But for our purposes, it is. But anyway, so the first part of this, he says, like, he does a pretty nice job of explaining this really complicated situation. So the first thing they do is they say that there's 4 characteristic length scales that we've already talked about. So those are the no, this is size scales. Sorry, 4 characteristic size scales. So we have the Kuhn length, which he calls a monomer. So he's mistaken there, but it should be the Kuhn length. Then there's a concentration blob, because he's going into the where he's above the overlap concentration. And then there's the tube diameter, which means he's above the entanglement concentration, right? And then there's the polymer coil size. There's 4 sizes. And that's as many, theoretically, that's as many as you can get. That's packed it out. I mean, you could probably invent some more, but basically there's 4, right? So that's good. And then the next section, he says that there's 4 time scales that are loosely related to those 4 size scales. So the 4 time scales are the below the Kuhn length, then there's the solvent viscosity. So you have basically that you're looking at, he explains it in here pretty well, but basically you're looking at the solvent viscosity below the Kuhn length. Then above the Kuhn length, you're looking at the Zim model, which means you have concentration blobs that are moving around. So he gets this tau. So this is so below frequencies higher than 1 over tau 0. That's when you look at the solvent. And then this is the concentration blob time scale. So you can see it correlates with this line here. So at the intercept of that, you get a different power law showing up over to the left. So that would be your Rouse behavior. So this is Zim here. Then you get to that size scale that has to do with the overlapping blobs. And then you get the Rouse behavior. And there's another time here, the entanglement time. So relaxation time and entanglement. And then below that, you get reptation for longer times than that. And then finally, you get the bulk solution motion, like the Einstein equation, like the intrinsic viscosity equation. It's complicated, right? So and also, so these axes can change. This could be G prime, G double prime, or the specific viscosity, or the compliance, or the complex compliance. And then this can be time or frequency. Right. So these plots can look completely different and talk about exactly the same measurement, same data, because you can plot it as modulus, viscosity, compliance. This you can plot as frequency or time. So the idea that you can plot this as time or frequency is called the Cox-Mertz rule. That you can take a measurement like his, so he does the cup and bob measurement, the Couette viscometer measurement. So that's a continuous flow measurement, and then he gets this plot. So he gets plot of specific viscosity. That's viscosity minus the solvent divided by the solvent. So if you divide that by concentration, you get the intrinsic, right? So he's going across concentration, so he doesn't divide by concentration. That's his parameters concentration. C over C star. So when that's 0, that's where C equals C star. So that's 1. And then at that point, this in specific is also 1. And that's where you see C star, the coils are overlapping, right? And then he tools along, and then he gets the entanglement here, some higher number, right? And I guess it's at about almost to 10 for the constant C by C star. And then he gets the whatever happens after that. This is let's see, this is this is the slope of this is the intrinsic viscosity when it's power 1. And then when it's power 2, that's where you have the Zim motion. That's the Zim behavior. And then this power would be like the Rouse behavior, right? That's where you see Rouse transport, whatever. So this is just continuous. You put a cup in a bob and you just spin it and let it keep spinning and you wait. So the slower you spin it, the longer you have to wait for it to reach equilibrium. So, or let's see. Yeah, the slower you spin it, you have to wait like an hour. If you spin it fast, it reaches equilibrium quicker, right? So basically, you're going to wait until it reaches equilibrium, then read the torque on the thing, get the viscosity from that. Do the same thing with the solvent, subtract the 2, divide by the solvent, and get this in specific. At different concentrations, get each of these dots. That's one measurement that he does. So here, this is actually looking at it in terms of time. And then he's going to do the same material and put it in cone and plate and oscillate it maybe 1% range of 2 pi, so whatever that is. So just a small oscillation distance, but high frequency, right? So you can go, then you can get the viscosity versus frequency. Then that's going to be a different plot, right? So the Cox-Mertz rule says that you can convert those two. The time 1 over frequency is time, and then you can just put those 2 plots on the same plot. And Wagner shows that here. He does that pretty well somewhere in this. Like, I asked a question about that. The Cox-Mertz rule. Figures 3 and 11 of this guy. Figure 3 says a lot to this. Yeah, it can be dry, but basically, so he does a steady state shear measurement is the straight line, and the dots are from his frequency measurement. And he converts it time 1 over times frequency, and they fall like right on top of each other. So one of these is just for pure PEO, and then 11 is for the mixture with clay. I think pitch figure 11 or something here. So this is with clay, and then they both work. So basically the Cox-Mertz rule works. I mean, it shouldn't actually really work. You know, maybe you could argue that it wouldn't work, but it does work. So that's the good thing about it. It means you only have to deal with one. No, there aren't 2 x-axes, there's just one. It's got to do with the idea that you have that response function, and there's just one function for any material. Like you hit the bell, it rings. If you hit the bell with drumsticks, or if you hit it with a bomb, it's still going to ring. It's just like responding in different ways, right? So it's the same bell. So that's the idea of the Cox-Mertz rule is kind of the same thing. You could hit it with a frequency, or you could hit it with a hammer, and it's going to have the same response. So because there's a single response function for everything that happens, that's why you can get modulus, compliance, viscosity from the same kind of basic theory, right? So anyway, you can see this is pretty involved. And it's completely kind of different than the way you look at things from a structural point of view. Like when you're doing static structure, crystallography and things, you don't worry about this stuff usually. Maybe you do with density functional theory at some point, when you get the dynamics of things are involved in it on a molecular scale. But usually when you pick up a chunk of steel or something, you don't worry about this kind of thing. You know, so plastic is different than that because it's got this kind of time dependence to everything. Anyway, so we get that, and then all right, so that's number 1 here. That's this thing, TCS, entangled regime, blah, 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 blah. And then he talks about passive measurements and active, like passive measurements is microreology. You're not moving anything, you're just sticking it in and observing the thermal diffusion of things. And then it's called microreology because you aren't using a rheometer that you can pick up, you're using these little beads, right? And then, all right, so there's another thing in the end. So this paper's got a lot in it, actually. It's got a real lot in it. So, and he does a pretty good job talking about it. So he goes to show this plot. It took me a while to figure this out. So he plots the bead size times the mean squared displacement is his y parameter, you know. So like, why is that? And I went and looked through all the equations. I thought, well, the bead size, anyway, so the reason is, and then there's a paper, he cites this paper by Rubinstein, who's one of the cohorts of this whole thing. And Rubinstein also shows the mean square displacement times the particle size for dynamic wave spectroscopy. You know, I'm not sure that Rubinstein actually does measurements. It's kind of a theory guy. So anyway, so why is he doing this? So basically, mean squared displacement goes with diffusion coefficient times time, right? That's diffusion, right? So in this DWS is looking at diffusion. From the diffusion, it gets the viscosity, but the diffusion of the probe particle is always Brownian motion. Okay, so that's going to be diffusion times time. Diffusion by Stokes-Einstein is going to be KT over 6 pi viscosity times the particle size, which is the probe particle size. So if you're going to look, in order to get access all this range, in the end, he's using different probe sizes that get the different frequency ranges, because the small particles move faster than the larger particles. So he has to use like 5 different particle sizes. So if you're looking at across particle sizes, if you want them to be on the same curve, you have to multiply the mean squared displacement by the particle size. Then you'll get KT divided by viscosity times whatever, 6 pi, and that's it. So you don't have to worry about particle size then. That makes it kind of more useful, right? So that's why this oddball thing shows up here. Because the particle size isn't important in the end to the analysis. That's just the probe you use. That's like I use that viscometer or that viscometer. Doesn't matter. Like you're still getting the viscosity out. So you want to remove that from the data. So that's why it's like that. That's not a question in the homework, but probably could have been. But I spent some time trying to figure that out, like why I was doing that plot. Anyway, so there's something I wanted to go through. 1044. Let's see. That I didn't go through last time. All right, there's a lot here, but let me just do that for argument's sake. So I want to just go through this thing. So if you go to the flow regime, right, then you say, I don't have any, I just have flow here. So I'm just going to say that the shear rate is viscosity. The shear rate times the viscosity gives me the shear stress. That's just the definition of viscosity. And then if the strain is the compliance times the stress, so that's how you define compliance, is that the stress equals compliance times stress, just like the modulus times the strain is a stress. So this is the compliance times the stress is a strain. If you have a fixed stress, you get a strain that changes. So the derivative of the strain with time is the derivative of the compliance with time times the stress that you have. And this is also the stress equals the stress times the viscosity. That means the rate of compliance change with time is 1 over the viscosity. Just by definitions, that's just the definitions of the terms. And if you say the compliance is the complex compliance. So basically the complex compliance is going to be a steady state compliance, and then so it's going to be made up of the complex numbers I, and then this frequency dependence, because that would be frequency times viscosity times time gives you 1 over. So that's just the definition of a viscous flow, is this thing, right? So if you convert that to modulus, so you take 1 over the complex compliance, you can see everything in this is like a mess, right? Everything in this whole subject, and this is the simplest possible part of it. But you take 1 over the complex compliance, you're going to have that thing, then you'll end up with this equation multiplied by viscosity times frequency. You'll end up with that equation. And if you want to remove that, you multiply by this minus I, you end up with this equation. So you have the real part of modulus and the imaginary part of modulus. And the real part is dependent on frequency squared, and the imaginary part's frequency. And that gives you the general rule in the flow part, that the storage modulus is rising much faster than the loss is rising. That means they cross. That means you get a crossover point at this frequency that's going to be like the ratio of the viscosity to the 0 plateau modulus. That's going to give you this cross point, because one's rising much faster than the other, and then they have to cross, right? So that's a crossover point of the thing, right? So that's what you expect for flow. And then the Rouse behavior, I'll have to go through this next time, but the Rouse behavior predicts that you're going to see frequency of the 1/2. So you expect to see power power 2 here, slope of 2. So 1 decade goes with 2 decades. So that's the slope here. Then for the 1/2, you expect 2 decades to go with 1 decade. So you have this weaker slope in the Rouse part. And there's a plateau modulus in between. That's like your standard. So that's basically your Maxwell model. That's what you look for a signature of the Maxwell model. And this is the plateau, and then this going up. Because he mentions Maxwell model in the paper, and he doesn't say like what he's looking at. So if you go to his, if you go down to where he's let's see, Maxwell-like behavior, and he's saying that this thing's showing Maxwell-like behavior because he's got a crossover. So he's got power 2 for the storage and a power 1 for the loss, and they cross. And then the storage reaches kind of a plateau. So basically that's Maxwell behavior. That's the signature in the storage in the modulus versus frequency plot. Right. That's why he says Maxwell behavior here. What else do I got here? Let's see. All right, well, that wasn't too hard. I don't think you got it, but basically, maybe you can look at it. That's 3, 4. There's a lot in this thing. See, I did that once, but that's not, I think that's mostly what I got here. What else is in this thing? He's got that business. Then he shows that he can get, this is a concentration, so he can shift these by concentration by these factors. See, he's got, so the Y and Z are shifting frequency and modulus to get the curves to lie on top of each other. And the numbers he gets for those match up with in the theory part of this paper. He goes through every possible power law dependence of time and modulus, and time and viscosity. So the specific viscosity versus frequency, and what are the power law dependencies for a good solvent and for a theta solvent. Good solvent he calls athermal, but basically it's good solvent versus theta solvent. And nu is 1 over df, so nu is 3/5 if it's a good solvent. Right. So from those he can predict. From this analysis, he just gives it. He doesn't do an analysis. The analysis of this is given by Colby and Rubenstein in their book. You know, if you want to look at it, it's in this chapter, which is cited there. So it's long and it's tedious. You know, I like to go through every possible condition in this thing. Oh yeah, this is where he has this thing, right? This is where he describes the microreology. So he does the DLS measurement. You get G2, you convert to G1. So we did that with dynamic light scattering, right? You get the correlation function. Then once you have G1 as a function of time, so that's just an exponential decay function normally, right? So we usually fit this with an exponential decay. In this case, because he's got so many particles, it's not going to be an exponential decay. So he's got an exponential decay as if you see one particle moving. But here he's got all the particles. You get scattering from one particle to another to another. This is the whole idea of DWS. You get this multiple scattering thing. So the length between particles is one of these lengths. He's got L. Let's see, you can't really see it here. It's too small. At least I can't see it. Here. So he's got L. He's got 2 numbers, capital L and small L. Small L is the distance between the particles. L star is the sample transport mean free path of the scattered light. In other words, how far is it between 2 particles before they scatter again? That's L star. And capital L is something to do with maybe it's the size of the particle or something. Capital L is some other parameter that you know from the experiment. So you have this, huh? The thickness of the sample. Okay. Plastic cuvette of thickness L. Okay, good, thanks. So anyway, those are 2 experimental parameters. The capital L you can figure out both of those numbers. And then you have this, you measured this thing on the left, then you can get this R squiggly T. Forget about what it is, but you can get it from that equation by fitting the time dependence of the correlation function. once you have R squiggly T, you can get, if you have R squiggly T as a function of time, you can get the mean square displacement as a function of time, the MSD, right? And then once you have the MSD, you can Fourier transform it to get the complex modulus. It's a series of really complicated mathematical things, but there's two fittings, then finally a calculation, and then boom, it pops out the complex modulus. The surprising thing is that it works. You can just dump a big cup of these beads into your goo, right? Stick it into DLS, measure the G1, plug it into these two equations, and then spits out the complex modulus. You do the viscometer measurements, the same number. It's a decade and a half of overlap with a mechanical measurement. This guy Weiss at University of Pennsylvania figured this out. I mean, at some point. Then other people, I guess, have been using it, right? So it's kind of like a magic machine. And I mean, you can go through the math and you can kind of convince yourself it's right, but there's a lot of pitfalls where it could be wrong, you know, but it turns out it's right. At least it's right enough that it matches up and you can use it. So, and it's the only way to generate, to match up with the theory that Colby and Rubinstein have come up with about all these details about all the different time regimes of the polymer, right? So that the fact that the two things were developed at the same time was kind of convenient, because otherwise they would have had this really convoluted theory that couldn't be proven, or you had this machine that measured something that no one wanted to see. So they made a demand for each other. So they both, it invented an industry, you know, within itself, because they could go to the same conference and say like this and that, and then everybody's happy. And then there's some company manufacturing the machines. Then like P&G, any soap company is going to have like a bunch of these machines. So you can charge whatever you want for it. Then they think that they can figure out how shampoo works from that. But it's going to really only work in solution polymers, like not in the polymer melt, right? So it's got to be like you're looking at paint, or in fact, there's a lot of industrial and medical things where you need to know this kind of information, right? So it is an industry that's pretty large. So you think that plastics is a big industry, but there's all these spin-off industries like that. Not spin-off, but they're actually industries in their own, you know. It's like paint and whatever, anything in solution, cosmetics. I mean, so you want to know how it's going to flow, and this is telling you exactly what's going on, right? So you can wildly guess and keep adding things and see until you get it right, or you can know what's going on and be able to predict it, right? So that's kind of the way to go. So I guess that's the theme of this thing. Hopefully you can see, though, it's good to be able to stand back and say, like, these guys are nuts. Like, why are they bothering to do this stuff? Like, so much intimate detail about these things. And many PhDs going through the details of this. And most of the people that write the PhDs don't have any idea, like, what they're doing. You get to the point where you don't have any idea. You're just doing this one little piece of this bigger picture, and who's guiding the ship? You know, the ship's just going randomly off into wherever. You know? So if you have an industry that's driving it, it's really useful, because then at least you know that you're going to that place. And maybe you won't get there, but you kind of go into somewhere. But if it's just academics driving it, this thing can go crazy. There's no one driving the car, you know. I mean, you could hit a tree. I mean, something bad could happen, right? So this is a pretty good example. I mean, I'm not saying it's useless, but basically, at some point you have to cut this off, right? And you can see these guys are still pounding away at this thing to get the intimate details of it. Anyway, so he does, I think that little ditty there, he describes the DWS better than any place I've seen it, because he just gives 3 equations. You don't need to know where these equations came from, and maybe no one knows where they come from. You plug the numbers in, you can get this thing, and it matches. He shows the data, it matches perfectly with the mechanical. It's like, basically, it's a magic machine, you know, that can do that. And it can get 1,000 times higher frequency than what you can get in a lab. So, I mean, it's pretty useful. There's other, I mean, so people have taken that kind of probe rheology, microrheology, and they've turned it, they do a lot of different things with it than just running DWS. So you can put like proteins on the surface of the particles and have them bind and look at how the transport changes with whatever, put a magnetic field on it. I mean, there's a bunch of different things. So a lot of young professors are doing that, like they're just doing microrheology and studying like different situations. So that's actually has some use, you know. That's actually pretty useful because you can study the dynamics of complicated systems using a probe molecule and then see how the interactions affect the viscosity of the whole system. And you can get a complex viscosity and something that's too complicated to put in a rheometer, right? So there is quite a bit of use for the technique. I don't know, maybe they'll win a Nobel Prize for the thing or something. I mean, if they get a little bit more medical application that cures cancer or whatever, then probably, who knows. It seems like it deserves it because it seems to be a pretty important jump in knowledge, you know. Anyway, so the questions here, let's see what I got a couple of minutes. Cox-Mertz rule. So the best place for that is Daga's this Norm Wagner paper, and he just shows it. He just shows that it works for both polyethylene oxide and for when you dump clay into polyethylene oxide. It's basically, it works for anything. If it can work for clay, so when you put clay, if you exfoliate, the clay normally is stacks, and you can put salts or acid in to separate the stacks. So it's called exfoliation. Foliate means like leaves, so you turn it into leaves that are floating around. Then they can, so they're floating around and you have a low viscosity fluid, right? Like a low concentrated 1% clay and water. And then if they sit around for a while, the ends of them theoretically link up somehow, or they can link up like that. And it says it can make a house of cards structure, and then it makes a gel over time. He shows that in here. He shows how the viscosity changes with time with these gels. Anyway, so basically it's an unknown structure that you can't show with scattering. Like no one's seen this house of cards structure. No one's, you know, so this is just conjecture from rheology measurements. Somewhere he shows the time dependence of in this paper somewhere, there's a plot. It's like time zero, it's Newtonian, and then just wait time, and then it gels up. I think it's like the first plot. I thought it was. Here, okay, so this is day one, and then as you go on, it makes it, see, it goes continuous. So just the viscosity just goes up, up, up. So finally it's a gel when it's just straight line, at least at that kind of time scale. So anyway, yeah, if you take that house of cards and you just shear it a little bit, you just go like that to it, like ketchup, you know. So it's a what do they call that? Shear thinning fluid, but there's a name for it. Anyway, so like ketchup, you hit the bottle and then it comes out, right? So this same thing, like if you just barely touch it, it turns into water. The viscosity disappears completely. You can turn it upside down, it's solid, right? And if you just tap it like that, it's water. It's kind of interesting material. No use for it really, but I mean, ketchup is something like that, so that has some use, I guess. But even though it's more of a hindrance than ketchup, theotropic they call it, right? Thiotropic fluid. Thiotropic means like ketchup. Yeah, so this is like ketchup. Anyway, so that's what they're studying. So Wagner's always doing something interesting like that. He's always got some thixotropic. Yeah, that's it. Yeah, you got it. Yeah. Anyway, so that's what this stuff is. So is that business? All right. So what was that? I was going to go through these questions. So Cox-Mertz, he shows it there. Equation 4. All right, I should have done this. Equation 4. So this is just one of those like do the diffusion thing. Let's see, wherever this is. Equation 1. Go 2, 3, 4. Okay, so he's got, so where does this come from? So time, and then where does that come from? We did this at one time. Oh, I don't have the notes from that though. So I remember where it comes from. This is the This is the Zim relaxation time. So that means the whole thing moves through the fluid. That's why it's size cubed. So the whole object is just moving through the fluid. Huh? Yeah, it's a Zim model. It's the Zim model, but it's basically just the intrinsic viscosity equation, I think. This has got to do with the volume, the displacement volume, and then this is the diffusion coefficient here, time times the diffusion coefficient. So time times time, let's see, time times D, and D is KBT divided by, okay, so let's see if I can do this right. So you have, let me write the equation first. It's tau of that blob size is a solvent times the thing cubed divided by KT, right? And then let me go over here and try to do it again. .cam. This is where running out of time that has an advantage, you know. It's like I don't remember how to do it. So you have the diffusion equations. You have the distance squared. Let's show. It's because it's probably not whacked out here. Let's write it here. We'll show it into trying to do it. Yeah. There. So you have that is the diffusion coefficient times time, right? That's Brownian motion. And then diffusion coefficient is KT over 6 pi viscosity times the size of the bead. So you end up with R cubed. If you kind of say that's the same R equals KT over viscosity times time, or tau equals R cubed over KT viscosity. So what we had? Yes, kind of. Right. So that's it. Got it. It's kind of fast, but anyway, we're out of time. But so that's just the diffusion equation. And then assuming that the mean square displacement and the size of the thing are the same thing. Right. And then if you know the scaling for this, the size of the blob, so this is a concentration blob. If you know the scaling of it, which is going to be nu over 3 nu minus 1, and then cube it, you get that equation. Like the blob size, the concentration blob goes with the concentration to some power. Right. And that's the power. So that's just plug and play. And then this NS over KT, he defined that as tau naught. So that's tau naught here. So this part is just what the, well, you don't need that part. This is the part I was kind of interested in. But no, you can get that part. You should get that part. You can get the other part easy. It's trivial, I think. I mean, he gives it earlier on. He gives that equation for what the squiggly thing is. So you can just frequent crossover frequency. So there is no crossover frequency for time temperature. It could just do the shift factor. But here he takes that crossover frequency and he uses it. So when he shifts by the two axes, he says the crossover frequency should be at the same spot. So the crossover frequency happens at this tau. So it should be that it happens at the same spot, I guess. Anyway, it works to do that. It doesn't exist in time temperature. So the concentration shift is different than time temperature. I think it's because time temperature is based on Arrhenius or Boltzmann kind of equation, exponential energy over KT thing. And this thing doesn't have an equation. So he takes a point instead. So I guess the point replaces the equation. Point relates two things. An equation relates two things. The point and the equation are the equivalence between the two, I guess. Anyway, probably ChatGPT would give you that same answer a lot faster if you plugged it in. So Maxwell, so I showed you what the signature of Maxwell was in that plot. And then the inset demonstrates Rouse behavior. So figure 9 just mimics figure 1. So if you look at figure 1 and figure 9, he explains figure 1 at the bottom of one of the pages. So if you compare figure 1 and figure 9, it's the same thing, right? And then he explains figure 1 somewhere down here. He goes through figure 1 step by step, you know. That's figure one, but it isn't right after figure one. It's like below, down here. So right here and to here. So this thing to there, that describes everything you need to know about figure one, right? So basically, this explains why figure 9 is the way it is and why figure one is the way it is. Figure one and figure 9 are the same figure. So this one's the experimental and the other's like the theory, I guess. Anyway, again, it's kind of a rabbit hole. So I guess it's good to kind of look at it and see, but try to not take it too seriously because I'm not sure. Try to figure out what the use of it is before you spend too much time doing something. Like, because it's good to be able to explain to somebody like your parents or your siblings or something like what it is you're doing. If you can't do that, do something else. Find something else to do because you've been convinced by somebody and you think that they know what they're talking about. And like, if you can't explain it to some little kid, like what it is you're doing, then rethink it because it might not really be worth the time you're putting into it. And it can be a lot of time. You can see these guys have spent so much time defining all these power laws. And like the thing's just a swooping curve, maybe there are no power laws. I mean, maybe it's interesting to them. It's a hobby, maybe, and who knows. So anyway, keep that in mind. So have a good break. See you in a week from Monday. Yeah.